Hello, in this video we're going to look at how we can convert from binary to the denary numbering system. So we get questions like this. We're given a binary number like 1011. How do I go from binary to denary? Well, binary is a numbering system which uses two digits, only 0 and 1. Denary is what we use as humans. So denary uses 10 digits, 0 through to 9. We also call this numbering system decimal. However, denary is often used by computer scientists because the word decimal often makes you think of a fractional number. So denary is what we typically call our numbering system. Now, numbering systems use different digits. Binary, only 2, 0, 1. Denary uses 10. This connects heavily to place value. That is how numbers work. We use place value to represent numbers. So for example, 712 is a denary number. Place value is, well, I've got a ones column over here, often called units in primary school. Then I've got a tens column. Then I've got a hundreds column. So really, 712 is not 712, it's 712 because I've got 7 hundreds, 110, and 2 ones. In all numbering systems, our place value is based on how many digits we have. The far right column is always a 1. Then we multiply by how many digits I have, which is 10 here, and you do that for every column. That's why the next column is 1,000. So in this video and the next few conversion videos, we need to keep that place value in mind for binary, denary, and also hexadecimal. So if given a question like this, I would start by writing out my number. And what we need to do is add in our place value for this number. Well, this number is in binary. So it's not going to be the same place value as denary. It's going to be the binary place values. So we do still always start with 1 as our far right place value. This time we're timesing by 2, not by 10. We now have 2 as our next column. 2 times 2 is 4. 4 times 2 is 8. So our columns with the binary place value keep doubling. And I'd always advocate drawing a table to represent this. So the top bit of the table are the place values. They're telling us what the digit is really representing. This 1 on the far left is really representing 8. This one here is really representing 2. Once I've got a table structure like this, to convert to denary, all I need to do is add up my place value when I've got a 1 written underneath. This is really saying I've got 1 lot of 8, 0 lots of 4, 1 lot of 2, and 1 lot of 1. So this number, 1011, is 11 in denary, and that is my answer. To look at another example here, I've got 0011, then a space, then a 1110. This is again another binary number. I want to see what this is equivalent to in denary. Well, first of all, a couple of things to point out. I've got a space here. We typically, when writing out long binary numbers, group them as nibbles and leave a space between the two nibbles, or more than 2 nibbles if it's even bigger. The space means nothing. It doesn't affect our place value. The space is only for us to read it more easily because long binary numbers blur together and are confusing. So just generally, computer scientists separate nibbles with spaces, not that it affects the number or how it's stored in a computer. And so that I've got a nibble on the left hand side here, I've added 2 zeros. Like in denary, zeros on the left hand side mean absolutely nothing. If I was to use 712 again and added a 0 on the left hand side, it's still 712. No matter how many zeros I add, these mean absolutely nothing. So when I copy out my number, I don't need to copy out the zeros on the left because they're not important. However, the 0 on the right is really important because it helps maintain my place value. So I do my table 1, 2, 4. I've got a bigger one this time. I'm going to keep doubling until I reach the end. So I go up to 32 in this case. I add my lines. I'm not very good at this on a graphics tablet, but there we go. And now I add up my column headings when I've got a 1 written underneath. Sadly, you don't get a calculator in paper 1, so I would suggest using a bit of mental maths and then actual workings out to not make a mistake. So 4 plus 2 is 6, plus 8 is 14, plus 16 is 30, 32 plus 30 is 62. And the last one, the biggest one yet, is this number here. So let's copy it out, 1101, 1011. At GCSE, you'll only ever get up to 8 bits, up to a byte. So biggest number you'll get is 255, which is good to know. The columns here, 1, 2, 4, 8, 16, 32, 64, and 128. Okay, the ones are blowing into my table here a little bit, but we're adding up 128 plus 64 plus 16 plus 8 plus 2 plus 1. And I trust myself to do this bit mentally in my head. So 3 plus 8 is 11, plus 16 is 27. However, certainly if I'm doing it in an exam, I would not trust myself to do the other numbers added together. So let's do this properly. 8 plus 4 is 12, plus 7 is 19. 2 plus 1 is 3, plus 6 is 9, plus 2 is 11, and 1 plus 1 is 2. The answer is 219. And if you're working out and gets a little bit messy like mine just did, I would always box it so the examiner can see it really, really clearly.